This is a problem set that will look something like what you could see for the IB exam. On the right-hand side, you'll see scores on some of them. Some of them I couldn't find the scores, but the rest of them, some of them I could. So what it means is for part A, that's worth 1 point. For part B, that's worth 2 points. And for part C, that's worth 3 points if you answer those things correctly. All right. So when you're doing the IB exam, that's something to remember. Something else, if you're taking the IB exam, and I would expect it in my class as well, just because when I'm looking at homework assignments, sometimes I'm not seeing a ton of work. I don't want you just to look in the back of the book and write down the answer, but you should be able to show me like notation to set the problem up, or at the very least the setup problem before you're putting it into your calculator. All right, so anything like that. So when it says like find the value of n here, which is in the center of this Venn diagram, you should be able to show me a couple steps before, if you're doing anything in your calculator, to help prove it. All right, so if you're doing binomial distribution or normal distribution on your calculator, you got to be able to show that little setup first, especially on a problem where it's like 2 points or 3 points on an IB test problem, because if it's a 2-point problem, they're usually giving you 1 point for the correct answer and 1 point for just the setup, just that quick little minute of writing down what you're putting in your calculator. So you could literally throw it in your calculator and write down the answer, and you're getting 50% on that problem. 5-0, that's it. So you have to be able to show that step. That's really important to show that setup step. Because on the IB exam, if the work's not there, then you just don't get any credit for it. You're just going to get the 1 point for the correct answer, and that's it. And if it's a 2 or 3 point problem, a 2-point problem, you're getting 1 point out of 2. A 3-point problem, you're getting 1 point out of 3. So you're really leaving a lot of points on the table. You're not going to be very successful on the IB exam if you aren't showing that introductory step. So very, very important to do that. All right. So we've got here on the review today, let's see, I think I have 1, 2, 3, 4, I think I had 6 or 7 problems, 5, 6, 7 problems from the IB exam. And then I did assignment 19 from your textbook. It's specifically like IB exam style questions. And I just pulled 6 of them from there. Again, these are questions that were actually on the IB exam at one point. And if you see a P1 or a P2, that just means paper 1 or paper 2. All right, that's what the P1, P2 means. And then your textbook has 3 marks, so it's saying part A is 3 points, part B is 3 points. All right, and that's what you can expect for the IB exam. Usually the paper 2 problems are a little more involved than the paper 1 problems. So on this assignment, I've given you 2 paper 2 problems and 4 paper 1 problems, just so you're familiar with them. And you'll see, yeah, some usage of the probability language that we've been doing. All right, things like that. All right, so.
And no, I don't want to be disruptive, but
yep.
Is this lesson today, is this going to be like what the test is going to be like? Not the IB exam, but like our actual test on Wednesday or Tuesday?
We'll have some problems that match this, but not the entire test, no. So this is just for those of you that are planning on taking the IB exam. I figured if we're going to do 2 days of review, I want one of them to focus specifically on what you should expect on the IB exam. Okay, that's really what I'm going for today. And the reason I staggered the review where I'm going to do the IB exam today, because I think these ones are a little more difficult than what we're going to see on Monday, because I think the IB questions tend to be a little more difficult. They're really hard questions to write. They literally have people sitting in rooms all over the world working on these problems for a full year and honing them in and making them better. So they're a lot better than questions I can ever write. That's for sure. So good question. Yes, go ahead.
Katie can't get into the room. Or no, not Katie, sorry, Chloe.
Chloe can't get into the room. Okay, did she get stuck yesterday too?
I don't think so.
Okay, weird. Okay, but she got stuck today. Okay, I'll email her real quick. Thanks for letting me know, Aaron. All right, so what I want you guys to do then, take a look at problem 1. I think this is a very approachable problem, first problem. I want you guys to work on this one. And honestly, it can kind of be like a self-work problem, work through these first couple. I'm going to go over all of them, but all 7 of them. But I think the first one is very much an approachable problem that I want you guys to try. So let Chloe know I'm going to send her the Zoom link and see if that works. Just one thing to keep in mind, whenever you see, typically when we see vocabulary that says write down, that one's going to be pretty straight up as just you're writing down the answer only. The weird thing is part C says write down, but it's a 3-point question, so you should show a little bit of work in part C. But part A and part A should just be a write down the number. Part B says find. Whenever you see the word find on the IB, that means they want you to show a little bit of work. And that's showing as well with the 3s here. So it is a little weird that this one says write down instead of find, but that's some vocabulary difference that you might want to see. Whenever you see find or show that, those are big popular words with IB. That means show your work a little bit. For this first problem, we have 30 students. That's the total sample size. 18 are fluent in Spanish. So we can say this is 18 minus n. All right, 10 are fluent in French, 10 minus n. And 5 are not fluent in either. So it turns out the Q is just equal to 5. That's your first problem there. When it says 5 are not fluent in either of these languages. The following Venn diagram shows that the event's fluent in Spanish and fluent in French. Now we have to find the value of n. So we know there's 30 students total, so there's a few different ways you can show your work, right? You can say that there's 25 inside the 2 circles. So that means you can say if we add all of the circles together, plus n plus 10 minus n, we should get 25. And that's one way to show your work. That step right there is enough to get you 1 point on the IB exam. That's it. All right.
I set it equal to 30. Is that okay?
Yeah, that's perfectly fine. One thing that the IB exam showed too was it said there's a couple ways you could do it. You could do that. You could also do the plus 5 equals 30. That's perfectly fine too. So either one of those would be a perfectly acceptable answer on the IB exam. And then when you figure it all out, you should end up getting n equals, was it 3, I think? That's what we came up to? Yeah. So n equals 3. And then the last part, write down the values. Again, because it's a 3-point question, I would be more comfortable doing 18 minus n and 10 minus n. And then 18 minus 3 equals 15. 10 minus 3 equals 7. And then just make it abundantly clear at the m. Hey, and m equals 15, p equals 7. All right, so put down your answers, box them up. That's how you're going to get full credit on an IB exam for one of these problems. So we could even make it a little more clear and just say m equals p equals. But when you're done with the problem, make sure you go back and your work, like if you're not the one doing the work, if you're just reading it, that it makes sense to you. And on an IB exam, they're typically given, like, this is what you want to look for in the answers, these types of things. All right, so even if your work's a little unorthodox or it's a little different, that's perfectly fine as long as you're getting to the same result and your work makes some bit of sense on the way. Okay.
Also, this is a random question.
Sure. All right. Problem 2, the following table shows the probability distribution of a discrete random variable x. So hopefully we understand this vocabulary now. The probability of the discrete variable equals whatever. And it's the probability of hitting a number, 0, 1, 2, or 3. All right. Find the value of k. Hopefully that one is not too bad. We should say 3/13 plus 1/13 plus 4/13 plus k equals 1. That's the first step. And then we should be able to add 3, 1, and 4. 8/13 plus k equals 1. K equals, on the IB exam, by the way, you get like an entire page, so you'd have plenty of room. I condensed it quite a bit. And I'm showing all of the steps. You don't need to show all of these steps for full credit on the IB exam. I don't think it's bad practice to show every single one of your steps, because if you make an error along the way, but you get 1 point for the setup, all right? 1 point for showing that you know how to solve it. 1 point for the answer. That's what you'll be looking for on an actual IB exam, okay, for this type of problem. Understanding that the probabilities all add up to 1 is key right there. Okay. Okay, that's what problem 2A is asking us to do. What about 2B when saying find E of X? And then remember what E of X stands for?
Expected value.
Exactly, that's the expected value of X. Okay, so we had to find the expected value. So for this one, let's see. Expected value. So let's see, they didn't give us any. I want to make sure when I wrote it down, I got to check real quick. I want to make sure I didn't miss a line, but they didn't give us any like value to say find it for 5 tries, you know? But I think in this one, what we would do is we would say, well, the expected value of X equals 0 is 3/13. And 1 try, the expected value of X equals 1 is 1/13. Just basically list them down, 0, 1, 2, and 3. I think that's what I would say for expected value for this problem. Like I said, I want to make sure when I was writing it down last night that I didn't miss a step. So let me pull it up from the old IB exam. Where's the probability? All right, so I'll look that up. While I'm looking that up, I want you guys to go ahead and start working on problem number 3. I'm going to look at 2B for you. All right. Now, problem 3, hopefully this one wasn't too bad for you.
Wait. Where did that just come from?
The expected value?
Yeah.
Sure. Sorry, so what it was is you do the 0 times 3/13. That's the probability of getting 0 time, or the outcome of getting 0 times its probability. And then we have the outcome of getting 1 times its probability, the outcome of getting a 2 times its probability, and the outcome of getting a 3 times its probability, and we found that probability in part 1, or part A. So even if you can't get part A, these problems are set up, so hopefully you can set up part B with the K, and you could still technically solve it with a K in there and get full credit for the problem if you couldn't figure out what part A was, that's kind of cool about IB problems. So I would just have, it'd be like 3K, so it'd be 9 plus 3K over 13 would be another appropriate answer if you couldn't figure out what K was. But yeah, kind of a weird thing to think about there. But that is possible as well. All right. Now, problem 3 is talking about this airport. The probability of A, all passengers arrive on time for a flight, is 0.7. Probability D, that the flight departs on time, is 0.85. So 2 completely different probabilities there. The probability that all passengers arrive on time for a flight and it departs on time, so this is the probability of A and D happening, is 0.65. The number of hours that pilots fly per week is normally distributed with a mean of 25 hours, standard deviation of, I forget what the Greek letter is called, but the standard deviation. 90% of the pilots fly less than 28 hours in a week. Okay.
What's the standard deviation?
Oh, it doesn't give it to you. It's going to ask you to find that in part D.
Oh.
Yeah. All right, so part A, show that the events A and D are not independent. So they're not independent. If they're independent, then their outcomes should have the same probability, right? So if I did the probability of A times the probability of D, all right, that should equal, if that equals the probability of A and D, then they are independent. So that one just goes back to they're independent if their probabilities multiplied together equal the same thing. So 0.7 times 0.85. And 0.7 times 0.85 equals 0.595. So these are not independent. And that means that when they're independent, that means that somebody showing up late to the airport doesn't impact the flight leaving late. But now this is saying that there is some type of impact on that. That's what the first part's asking. Okay, part A there. Okay. Part B, find the probability of A and not D. So let's start with the probability of D is 0.85. So the probability of not D is 1 minus 0.85 or 0.15. That's the first thing you want to recognize. And something just like as simple as that is going to get you 1 point. Just like, okay, we got 1 there. Okay. And now, excuse me, I have the probability of A is 0.7, probability of D is 0.85. So now the probability of A but not D. We can do the probability of A is 0.7, and then, what was it? What am I thinking here? I'm trying to think. I don't want to do this wrong, but I was going to say 0.7 times 0.15, but we would need to do an OR there as well. So I have to think about this. This might be easiest to set up a Venn diagram, a picture for it, when you're thinking about these types of problems. Sometimes they can get a little tricky like that. All right. Let me verify that I'm doing this correctly before I explain it to you. All right, so the probability of A. All right, and not D. Oh, that's the probability of A. Because if I do the probability of A, that's the probability that everyone arrives on time. And I subtract the probability of A and D. That's where I'm going to get the A and not D from. That's where I was doing that a little wrong, sorry. And that's because it's almost like a given problem. It's given that A is happening, now part D is going to happen. Okay. So what we do then is we say the probability of A, 0.7 people arrive on time, minus the probability of B is that 65% of those flights are going to leave on time. So you're going to have 5% of the time basically where people show up on time, but the flight still leaves a little late, which I feel like that seems kind of low. But that's the idea for part B there. So actually, the whole thing I did at the beginning, just a little off. Sorry, I was thinking of it the wrong way. I was thinking about it if they were independent events, but since they're not independent events, that's what we did in part A. That's what allows us to do the part B part. Okay, if they were independent events, then we would multiply the 0.7 times the 0.15. All right, so I apologize for screwing that one up a little bit there.
So how does that give you the probability of A and D not?
Oh, how does this one give us that? So what it is you're saying the probability of A happens and it's a given. So the probability of, because the events are not independent, so the flight leaves 65% of the time when the passengers are on time. Okay, so then what you say is, okay, well, if it leaves this much of the time and there's 0.7, then we can do the 0.7 minus the 0.65. So I'm not explaining that well. Let me back up. Excuse me.
Wait, did you solve for part C on that one?
That was part B.
Yeah.
Yeah. So no, what part B is asking us to do is you have, so 0.7 is the probability that you show up to the airport on time, and you showing up to the airport on time affects whether your flight leaves or not on time. So they're saying, 65% of the time your flight will leave on time and you'll show up to the airport on time. But that 65% takes into account the fact that you're not always showing up on time. So that's why we're doing the 0.7 minus the 0.65. And we're getting the 0.05. That's saying you're showing up on time, but your flight is still not leaving on time. That only happens 5% of the time, where
So
all the passengers are arrived on time, but the flight's still not leaving on time.
So that's the same answer for part C as well.
Part C is a little bit different.
Well, it's that all passengers arrive on time and the flight doesn't depart on time.
Oh, am I looking at the wrong one? Find the probability the flight does not depart on time. Yeah. Let's see. I think this one's, let's see, given that all passengers for a flight arrive on time. So this one's given that they arrive on time. That's going to change the total probability. So this is D given A. So what's going to happen is we're going to need to do the probability of A in the denominator. And the top will be the probability of A and not D. So it's slightly different because before on part B, we're just doing A and not D, and that's just given everybody, the entire sample size, even the people that are showing up late, impacting the flight. Now we're saying given that everyone was on time, what's happening? So it's a little different in part C. And this is what makes probability so freaking hard, is that it changes just a little bit when we have a given circumstance. So we would take that probability we found in part B and divide it by the probability that everyone was on time, the 0.7. And we're going to get something like 0.0714. Something like that. Yeah, so those ones are kind of a pain. But that's the idea there. Okay. Okay, next, we have find the value of the standard deviation. So the number of hours that the pilots fly per week is normally distributed 25 with standard deviation 90. That one is that's an AA problem. We don't actually need to do this for AI because we didn't talk about how to find standard deviations. So that is that's a crossover problem from the other class. So don't worry about part D. Sorry about that if that was confusing to people. Okay. And then let's see, part E is going to require part D as well. So we're going to cross out part E. I apologize for that. I need to be a little more careful. But parts D and E, those are crossover problems from the other course that we did last year. So those you would not see anything like that on your IB exam. All right. When we're doing normal distribution, the only thing we're going to do is that calculator application problem that I showed you guys yesterday. So we don't need to worry about that part there. Sorry, when I read it, it just looked like a good normal distribution problem. But yes, sorry about that. Okay. Problem 4. Today Philip intends to go walking. The probability of good weather is 3/4. If the weather is good, the probability he will go walking is 17/20. If the probability is not good, the probability he will go walking is 1/5. So we'll fill that in 1/5. Complete the probability tree diagram to illustrate this information. So we have a 3/4 probability he goes walking. That means there's a 1/4 probability he doesn't. And then over here we'd say 3/20. And then down here there's a 4/5 chance he does not go walking if it's not good weather. What's the probability that Philip will go walking? So now we just look for that it's good weather and he goes walking, or it's not good weather and he goes walking, and we're going to add those two outcomes together. 3/4 times 17/20 plus 1/4 times 1/5. All right. And then we just put them together. So 3 times 17 is 51. That's 51/80ths plus 1/20. So I think we should get 55/80ths here, or we can turn that into a decimal. I'm not sure what the decimal is off the top of my head, but that's the idea for this one.
Can we just keep it as 11/16?
Yeah, sure. Oh, you got 11/16? Perfect. Oh, yeah, because it simplifies. Yeah, leave it as 11/16. That's perfect. Okay. Good. Yeah, because you can divide both by 5. Good. All right, that's problem 4, but that's an IB question. This is probably a paper 1 question right here. All right, problem 5. On a particular day, 100 children are asked to make a note of what they drank that day. So we have to represent a Venn diagram. And this one is a great example of they really make it very clear what they want you to do with the Venn diagram, which is really nice if you ask me. You're going to get your circles going, and then we'll label them. Our total sample size is U. We'll do water, coffee, fruit juice. But they say like one child drank only water. So that makes it very clear. Only one in that category. You don't need to do anything with the X's or subtracting. 6 children drank only coffee. 8 children drank only fruit juice. 5 drank all 3. 7 drank water and coffee only. 53 drank coffee and fruit juice only. 18 drank water and fruit juice only. And then it says on a particular day, there were 100 total children. And that's what part B is going to ask us to do. How many children drink none of the above? So we're looking for the number that goes out here somewhere. All right, so we can add all of these together. So we can call this the drink none. We'll just call it like an N or something. And we'll say 1 plus 7 plus 5 plus 18 plus 53 plus 6 plus 8 plus N equals 100. And then we're going to subtract everything from there. Okay. And what do we end up getting for our N value on that one? 8.
2.
N equals 2. Perfect. So 2 kids that didn't get any water. Okay. Or anything. All right. And then part C is just setting up those probabilities. A child is chosen at random. Find the probability that the child drank coffee. Well, we have to count all of them out of 100 children. 6 plus 7 plus 5 plus 53. And this is as simple as it is to show your work. Just show that you're adding all the C values together, and then you simplify it, and that's your answer. 13 plus 5 is 18, plus 53, 71 out of 100. Does that sound right? And then part 2, water or fruit juice, but not coffee. Okay, so water or fruit juice, but not coffee. So that's 1 plus 18 plus 8 over 100. All right. Because it doesn't necessarily exclude them if they drink both. All right. So that's 9 plus 18. That's going to be 27ths over 100.
Wait, how did
Add the 2 children that didn't drink any of them.
How did we get these 2 that didn't drink any? Oh, so we added all of the numbers in the Venn diagram together. So it should have been 1 plus 7 plus 5 plus 6 plus 53 plus 18 plus 8. I did not double check it. Is that number wrong?
No, it's right, but I'm saying for the question of like the. Oh wait, never mind. I messed up. Never mind.
Okay. And then part 3, now this is a given one. It says, given that the child did drink water, that's going to change our probability in the denominator. They did drink water. That's 1 plus 7 plus 5 plus 18. What's the probability they did not drink fruit juice? So that's the 1 plus 7, because the 18 and the 5 would be taken out of that. All right, and that's what we do for this last problem. So we should get something like 8 out of 8 plus 5 is 13 plus 18, 31. 8 out of 31 for that last one, I think. But that's the idea when we change the probability of the denominator. All right, we're saying, given this new circle, we're only going to work inside this circle now of the Venn diagram. But
wait, I want to like make sure I understood that.
Sure.
So
No
it's
problem.
the 1. So on the bottom, that's the probability that the child drank water.
Yes.
So that's like all of the water. So 1 plus 7 plus 8, 18 plus 5.
Yes.
And then no fruit juice. That's just the 7 and the 1.
Yeah, but then they didn't drink fruit juice. That's this one and this one, yeah. Because 5 and 18, they had fruit juice, yeah. Okay, that's the idea. But yeah, the key here, though, that you're seeing on these problems, if you're ever asked to set up a Venn diagram, they're going to hopefully make it very straightforward to you if they're going to ask you to use that Venn diagram for the rest of the problem. So that's kind of nice. Okay, now we have 2 children who are chosen at random. Find the probability that both children drank all 3 choices. So the first child, if you choose a child at random, there's 5 in 100 probability that that child drank all 3. The only other option now, you have 99 children left, and there are only 4 that drink all 3. So you just do 5 over 100 times 4 over 99. So 20 over 9900, and then you can put that in your calculator and you'll get some really small decimal. I mean, it should simplify it to 2/99ths, right? But yeah, I would say just throw it in your calculator and you'll see what you get. Okay.
I got 1 over 495.
Sure. Yeah, that sounds good. It's gonna be a very small number. It's like 0.00202. Yeah, that makes sense. Yeah. And as long as you show the setup and you leave it as a fraction, that's perfectly fine. That'd be an acceptable answer. If you simplify it to 1 over 495, that would work too. All right. Let's see. Oh, shoot, it's 11 o'clock. Dang it. All right, well, if you guys got to get going, have a great weekend. I'll finish these last 2 problems and I'll post this on the Canvas page. I apologize for running over today. Where did the time go? Went so fast. All right, but I'll keep working on these last 2, and like I said, I'll post this on the Canvas page. I apologize for going over today. All right, so problem 6, children in a class of 30 students are asked whether they can swim or ride a bicycle. There are 12 girls in the class. 8 girls can swim. All right, 6 girls can ride a bicycle and 4 girls can do both, so they've already filled it in for you. 16 boys can swim, 13 boys can ride a bicycle, and 12 boys can do both. All right. This information is represented in the Venn diagram. Find the values of A and B. So again, we're saying there are 12 girls in the class, and we said 8 girls can swim, and I see right now 8 girls can swim. I only see 4 represented on there, so that means this A should be a 4 as well. All right, and that's literally it when we're trying to find these values here. 6 girls can ride a bicycle, and 4 girls can do both. All right. Next, we have the boys. It says 16 boys can swim. All right, so we have 12 and 4, that's 16. 13 boys can ride a bicycle, and 12 boys can do both. So that means there's 1 boy that can ride a bicycle, but can't swim. All right. And again, we're looking at this. This one's kind of a weird one because it's got the line that separates the boys from the girls, but that's kind of the key there for reading this one. Calculate the students who can do neither, so we go to 30 students total. What's up?
For A, what is the number like of girls add up to 12 because there are 12?
Yes, it should add up to 12. Exactly right.
Only adds up to 10, but I assume those 2 left over are the girls that can't do any of it.
That's what I was thinking, but I just wanted to double check.
No,
Yeah.
you're absolutely right on it. So you're both correct. So yeah, so those 2, there's probably going to be 2 outside, and we're going to figure that out right now. So we could say 30 minus 4 minus 12 minus 1 minus 4 minus 4 minus 2. And we'll figure out how many students fall into this category of neither. All right. So minus 12 is 18, minus 4 is 14, minus 4 is 10, minus 4 is 6, minus 3 is 3. So there are 3 students that can't do either. And you're right, it's going to be 2 girls and 1 boy. We can figure that out logically. And now you're absolutely right. We can also go back and check at the very end. So there are 12 girls in the class, which means there should be 18 boys. And now we can count it up. We can say 4 plus 12 is 16. And then we had plus 1 is 17, plus 1 is 18. That checks out. And the girls, 4 plus 4 plus 2 is 10, plus 2 is 12. So those numbers do check out. Now write down the probability the student chosen at random can swim. So now we're just looking at this entire swim circle. So there's 30 total. 4 plus 12 plus 4 plus 12. Or plus 4 plus 4. So 24 30ths. Or you can simplify that. If you divide both by 6, you're going to get 4/5. Okay. Now, given that a student can ride a bicycle, write down the probability the student is a girl. So kids that can ride a bicycle, 12 plus 1 plus 4 plus 2. That's the denominator. And then the numerator is going to be a girl, and there were 12 girls. So we just put 12 on the top. We're going to get 12 over 13 plus 4, 6, 19. 12 19ths. All right. That's what problem 6 is going to look like.
Wait, why did you put 12 at the top?
Because write down the probability the student is a girl.
Oh,
wait, sorry. Given that they ride a bicycle, I'm sorry, right?
yeah.
That's going to change the number a little bit. Because it's only girls that can ride bicycles. It's not total girls. My apologies. So it should be 6 19ths. You're absolutely right, Aaron. Small mistake there. 6 19ths, not 12 19ths. Because there's 6 girls that can ride bicycles. All right, we got to stay inside that bubble there.
You should correct that on the left side.
Yes, thank you. All right. And then the last problem here, number 7. There are 15 names, and we know that 3 of them begin with the letter B, and 4 begin with the letter G. Everyone else, the remaining 8 names, begin with those different letters, respectively. The 15 names are placed in a box. The box is shaken and 2 names are drawn out. Find the probability of each. So this is a dependent situation because you're drawing one name out, then you're drawing the next name out. Both names begin with any letter except G or B. So there's 8 out of 15 the first time. And the second time, there's 7 out of 15, right?
Wouldn't it be 7 out of 14?
7 out of 14, yes, thank you. 7 out of 14. All right. And then that's the first problem. We should get 56 out of 210. And that simplifies to 4/15. We can turn it into something else. Now, we have the probability that both names begin with the same letter. So we said there were 3 that start with the letter B out of 15. So that's one possibility. You have 3/15 and 2/14. Keep doing that. And the other possibility is you had 4/15 times 3/14.
But isn't that the same for like every, like you'd have to do the probability of every single one of them? It'd be like 1/15, 1/14 plus, like you'd have to do the whole thing.
No, because you're only drawing 2 names, right? So if they have the same letter, they either both have a B or they both have a G based on the information we were given at the very beginning. So the probability.
Oh, because there's only one of each.
Yes.
The other ones. Oh, okay, gotcha.
So there's only one of each of the other 8. So the probability that they both have a B is this right here. The probability they both have a G is that right there. So you just add those 2 probabilities together, and that's where you're going to get 6 out of, what's that? 15 times 14 become? I don't remember. That's 210. Yeah, 210
Oh, wait.
plus
I did that wrong.
12 over 210. So you should get 18 out of 210. That should be your chance, right? That should be your probability of that happening right there. Or it simplifies to 3 over 35. And then the last one says, both names begin with the letter H. This one is a probability of getting an H twice is 0. There's only one student with the letter H. All right, so only one student with the name starts with the letter H. So that's all you'd have to say for part C there. But hopefully those IB problems are not crazy tricky. There are some of them that are tricky, and I think the hard part is when you're not studying probability actively and you come back to it on the test. But this is a lot of probability problems. This is over several years of IB tests. You're probably going to get 1, maybe 2 probability problems on the actual exam. Okay?